by the time we're done, what I want to be able to do is I want you guys to be able to understand these diagrams I have here. I want everybody to be able to understand exactly what they're looking at, so that this is not complete gibberish just to you guys. And so by the end of this, by the end of the day, you should be able to look at this and know what this is talking about, what's going on here with these diagrams. But fundamentally, as far as the blockchain, it's just a data storage mechanism. And with relation to Bitcoin, what we're doing is we're every chain except for the original Genesis block, every block in the chain has inputs and outputs. Okay, and so the inputs are your transactions, and the outputs are what we call unspent transaction outputs. So that's what's left over available funds in each wallet that had transactions in that block. And then there's a step to validate and secure those blocks, and then these blocks are linked together cryptographically. So let's get straight to the white paper now, and I'm going to take a quick look. Guys, feel free to ask questions as we go. I will be I'll be pausing at the end of each section to just make sure I answer any questions so that everybody is clear as to what we're talking about. Now we go to the top here. Bitcoin, a peer-to-peer electronic cash. Oh, wait, taking a sip of coffee. Very good. Took another sip there, sorry. All right, Bitcoin, a peer-to-peer electronic cash system by Satoshi Nakamoto. Quick note, I personally believe that Satoshi Nakamoto is a pseudonym for a group of people. I think the orchestrator of the group was Hal Finney, who was the very first person to download the original code once it was uploaded, and the first person to receive a transaction from quote-unquote Satoshi to himself, which he never paid back, interestingly enough. Now, if I was building a brand new protocol, I would want to test out the first transaction by sending something from one of my wallets to another wallet I control to make sure it works, and I wouldn't care about paying myself back because I'm the same person. But I think he was the orchestrator of a group of people, and I'll talk about that as we go through here because I think that's also interesting to keep track of. All right, abstract. So this very first paragraph tells you really everything that you need to know at a very high level summary. But Bitcoin is a purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. So there's a need for trust with a bank or any other middleman whenever you transfer any financial transactions. And so they're trying to remove the need for trust and put that into computer code that everybody trusts the code as opposed to trusting a third party, basically. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. So the double spending problem was digital currencies have been around for a long time. They've been proposed for 30 years before this, roughly. What this paper really outlined is a way to solve, one of many ways to solve this double spending problem that can happen with digital currencies. Basically, in short, there's nothing preventing me from doing multiple transactions in the same in a short period of time, and then the network not being able to do anything about that. So now notice I highlighted we here. This is also why I think that Satoshi made it pretty clear in the way that he worded some things. And the person who wrote this, it's not an individual. You can tell by the writing as we go through here. The different sections are actually written slightly differently. There's an editor that has a common theme, but it's mostly British English, but there's definitely some American English way that they put things together. So there's multiple people that had input on this paper. We proposed a solution to the double spending problem by using a peer-to-peer network. So a network of connected computers. They're not directly connected as you would have at your cable physically connected, but a peer-to-peer network as in we have a soft adjacency, just like if you've ever downloaded anything from a peer-to-peer like torrent-based network. The network timestamps transactions by hashing them onto an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. Now, hash-based and proof of work are probably terms that not everybody understands. We're going to explain those as we go along. Now, for people that are in technology, this network timestamps doesn't mean like network time server or like a centralized time server. It's a rough time system. So it's a time system based on the validating of blocks. And we'll talk more about that as well. And feel free to post questions as we go here. The longest chain not only serves as proof of sequence of events witnessed, but proof that it came from the largest pool of CPU power. This is important. As long as a majority of CPU power is controlled by nodes that are not cooperating to attack the network, they'll generate the longest chain and outpace attackers. Now we're going to demonstrate this later to help you fully grasp what this means. But basically, as long as 51% or more of the network is controlled by people that are behaving properly, the network will be secure. If anyone gains 51% of the compute power, they can game the system. And with the paper, we'll talk more about that later. But fundamentally, the hashing power of the Bitcoin network is so monstrously big, the ability of somebody to coordinate 51% is very difficult right now, near impossible. And even if they did coordinate 51%, there's limited damage that could be done. And we'll talk more about that as we go along. The network itself requires minimal structure. And it's actually a very simple system, which is very good. Messages are broadcast on a best effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of whatever happened while they were gone. All right, moving on. Let's see if we have any questions. Thanks, Kevin. Introduction. Commerce on the internet. Make sure, yeah. Let's move up a little bit. Commerce on the internet has come to rely almost exclusively on financial institutions serving as trusted third parties to process electronic payments. While this system works well enough for most transactions, it still suffers from the inherent weakness of the trust-based model. Completely non-reversible transactions are not really possible since financial institutions cannot mediate disputes. The cost of mediating increases transaction costs, limiting the minimal practical size, so forth and so on. I'm going to skip ahead here. You get the idea. They're outlining problems with the traditional financial system and some issues there. So he goes on to say, or they go on to say, what is needed is an electronic payment system based on cryptographic proof instead of trust, allowing two willing parties to transact directly with each other without the need for a trusted third party. I think you guys get that idea. Let's move on. Transactions. We, plural, define an electronic coin as a chain of digital signatures. Each owner transfers the coin to the next by digitally signing a hash to the previous transaction and the public key of the next owner and adding these to the end of the coin. A payee can verify the signatures to verify the chain of ownerships. All right, that's a mouthful. People who aren't in technology, I have a note here to two things. So we have this diagram we're going to talk a little bit about. But you see, this is a diagram diagramming the change of ownership. This is not necessarily blocks per se. This is just a diagram outlining how the change of ownership happens. So, owner 1 owns some funds, or owner 0 owns some funds, really, and he sends those funds to owner 1. So when that transaction happens, owner 1, or am I getting this right? But owner 1 would sign a transaction with his signature. So owner's 1's public key is let me back up. Owner 0 sends funds to owner 1's public key. And then when owner 1 sends funds to owner 2's public key, he signs that transaction with his own signature, using owner 1's private key, and so forth and so on. So every time one owner transfers value from himself to another owner's wallet or public key, how the network verifies this is the owner of the funds prior validates every transaction with their private key. Now, if you want to know more about what private keys are, let's go back to our little diagram here. I outlined this in a video that I did. The video was called, hold up, if y'all can see that. No, it's on the wrong side because my mug is in the way again. A video is called "Crypto Wallets Oversimplified," and here I described what a public key is and how it works. So please refer to that video for a better explanation on what a public key is and how it works. But basically, you can think of a private key as the secret that is shared in relation to like a decoder ring. And so basically, you can think of it as like a decoder ring, more or less, in that whole system. Well, my video. Crypto Wallets Oversimplified explains it, starting at 1 minute 30 seconds. What is a private key? Now, I also have a note here to describe a hash. So a hash is the result of some mathematical computation that the computer does, and it generates basically a shorthand notation of some information. So it's a lot to say. Let's demonstrate that. Any questions so far? This is awesome. Hi, Brandon. 2 million ETH stuck. Yeah. Well, we'll get into charts and technicals some other time. Right now, focused on, let's talk about, maybe if we have time at the end, we'll look at that. All right. So here is, oh, where's my hash demo? Oh boy. Did not put that. Blockchain Explorer, blockchain demo, hash demo. Oh, sorry guys, hold on. Not the blockchain, I want the hash demo. This will work. It's not the one I had in mind to pull up. I'm sorry. Messed this up, didn't I? All right. So if I take some data here, so say CTM rocks, you see as I type, it spits out, the hash is constantly changing. The hash is a fixed length. So the way that the math works, what happened, this is a SHA-256 hash that's being spit out here. So whatever the input is, the computer does some calculation on that basically, and it spits out a fixed length hash. And this is the hexadecimal value of version of this hash value that's being spit out. But I can type in, but notice it's every single letter that I change. So if I do CTM rocks, which is conquer the markets, that's the hash value you get. Starts with 9E5 and ends with B43. If I remove the exclamation point, it changes entirely. And if I go change it to the crypto trades and tech, rocks, totally different string. Every letter that I change changes the string entirely. So one small change to the input changes the hash dramatically. That's the main thing to understand about this. And that hash can be referenced to validate. Now the way this is done asynchronously. So that hash can be verified that it was this owner that actually signed it based on that owner's. So you can use their public key of an owner to validate that their signature was indeed valid. So can the private key be hacked? So Henry, the private key, it's so if you have somebody's public key, it is nearly impossible. It's not impossible, but it is nearly impossible for all intents and purposes. It is impossible to hack a private key using like just brute force attacks. It would take something along the lines of 100 years of the entire computing power of planet Earth to break a SHA-256 key right now, and you'll understand why more as we go along here. But it can be stolen. So that's the thing. So in that video that I did as well, if you go Crypto Wallets Oversimplified, I talk about why we have to keep our private keys secure, because they can't really be cracked per se. For all intents and purposes, they can't be cracked. SHA-256 anyway. There's no known easy crack for it today, and it's been around a long time. But they can be stolen. All right, this is a mouthful, but that's how we transfer ownership. Is from one owner uses their private key to cryptographically sign a transaction to change ownership. Okay. And then I had another note on here. Okay. So down here we see the problem, of course, payee can't verify the owner did not double spend. We need a way for payees to know that the previous owner did not sign any earlier transactions. Move this up as I go through this. So the note that had to accomplish this without a trusted third party, transactions must be publicly announced. So this is another thing. It's a public ledger, right? Everything that happens on the Bitcoin network is completely public. Now, the white paper will talk about more about this later. The way that you can provide some anonymity is that you just don't, you set up a new wallet address that's unknown to the world. That doesn't have any known information about it, and then transfer money to that. But it's a public ledger, so people can figure out who you are and what funds you have if they spend enough time studying that ledger, fundamentally. We need a system for participants to agree on a single history of the order in which they were received. This is called consensus. So they need a consensus mechanism. So if you hear in other crypto terms and other projects, you hear about consensus mechanisms. This is what this is. A consensus mechanism is simply a way that for all participants to agree on a specific a set of transactions at a particular set of time, or to agree on something. They all have to agree at some point in time the state of the network or the state of the system, and that's consensus. And so that happens. Consensus is an ongoing thing, right? Because things are constantly changing. So you take a snapshot. At this point in time, everybody agrees that this is the state of all the transactions on the system. And then the transactions continue, and then you lock those up, and you run consensus again, and you continue to maintain consensus. This is what consensus is. All participants need to agree on a single history. Okay? Do you have any notes about demos here? No. Moving on. All right. Let's see if we have any questions. So you're saying there's a chance? Yes. I like it. There's a chance. It can be cracked too. Quantum cryptography. We'll talk more about how the longer the network has been running, the more secure it actually gets. So both the hashing power and the length of time it's been running both provide security to the network. So the Bitcoin network's been running for quite a long time. It would take a lot of compute power to go back and change transactions historically, because you have to recompute everything, first of all. And second of all, the more mining power there is, the harder it is. Now, quantum cryptography could change that. But there are quantum-resistant crypto ciphers. So maybe a whole other video I'll talk about quantum cryptography and quantum computing. It's a topic I spent way too much time studying at one point. All right, timestamp servers. The solution we propose begins with a timestamp server. A timestamp server works by taking a hash of block items to be timestamped and widely publish the hash, such as. We're going to skip that. Each timestamp includes previous timestamps in its hash, forming a chain, with each additional timestamp reinforcing the ones before it. So this describes the absolute fundamentals of a blockchain, right? It's a series of chained together. So a timestamp is basically a block is a timestamp, right? So a block is it takes about 10 minutes for somebody to solve the next hash to be able to confirm that those transactions for that block. And so these blocks are chained together cryptographically, and we'll talk a little bit more about that when we do the demo here in a minute. But this is the basic fundamentals of the blockchain. So it's a chain of blocks that are hashed together cryptographically, such that if you want to change, so right now we're at block 650,000, whatever it is, the block depth. If we look at a current 664,037. If you want to change a transaction back on block 500,000, you have to recomputate 500,000 to 664,000. All those blocks faster than the network is adding new blocks, which is never going to happen. So that makes those prior transactions even more secure. Proof of work. Now, this is where we get into an explanation of what that is. To implement a distributed timestamp server on a peer-to-peer basis, we'll need to use a proof of work system similar to Adam Beck's hash cache. So it's using a hash cache proof of work system. The proof of work involves scanning for a value that, when hashed, such as with SHA-256, the hash begins with a number of 0 bits. The average work required is exponential, and the number of 0 bits required can be verified using a single hash. So, let's go look at. Pull up the Blockchain Explorer real fast, and I'll show y'all what this looks like. So if I pull up this block, so this is a block that was mined about 2 hours ago. That was validated about 2 hours ago. Now you'll see the hash of this block is this up here. If you can see that, yep. Notice the leading zeros. So what makes mining difficult is that you're trying to find, and all the trillions upon trillions upon trillions of possibilities for this output of numbers here. You're trying to find one with a leading set of zeros set by the protocol, set by the Bitcoin network. And the first one that finds a hash now there are trillions upon trillions of hashes that will work. It's the first person that finds one with this number of leading zeros is the one that wins for that block time. Okay, so if I had a hash and I had this many zeros and I was missing whatever this last zero, and say this zero was the number 2, well then I haven't solved it. I got pretty close, relatively close. Now every zero is exponentially harder to solve. So when we adjust the mining difficulty, every time you increase this by 1, it makes it exponentially more difficult for the network to solve it. So but nonetheless, what the miners are trying to do is create a hash with this many leading zeros, and that becomes the block value. Okay, that's kind of complicated. When we demo it here in a minute, you'll see that more clearly. For our time-step network, we implement a proof of work that increments the nonce. So a nonce is just a random number. It's kind of important to understand, but this is what the there's two main things that a miner is monkeying with to try to come up with a hash value that starts with this many zeros. Now, if you notice, I can put all kinds of stuff in here, and it would take me a very, very long time. Let's see how many times I gotta mess with this just to get a zero at the leading end here. It would take a really, really long time to get a bunch of zeros at the beginning of, a block. Just trying all the different values. I think I had 0 here a second ago. But it takes a lot. I had a 0 right there. So I got 1 0. So now, if for me to find a combination of words that would spit out in such a way that I create a bunch of zeros, I'd be here typing like that monkey theory for, a billion years or something. So it takes a long time. And so what the miners are monkeying with, though, the combination of information they're monkeying with is the nonce is a part of it. So the nonce is a 32-bit number. So it looks a lot like an IP address, but it's a 32-bit number. And then there's some data that's related to the tree structure of how the block is organized. So pretend that's the data I'm trying to find a nonce. I'm sitting here monkeying with these numbers over and over and over again to try to find a nonce that produces a hash with that many zeros. And at the same time, if I go through all the possible nonces, which there's 4 billion, so a 32-bit number, there's 4 billion possible combinations. If I don't find a match with this data set that I've constructed, then I have to reconstruct this data set. I got to move something around here. I'm going to reconstruct my tree, and I'm going to try again from, 7 zeros or 8 zeros and 7 zeros and a 1, and then 0, 1, 0. And I'm going to keep trying until I figure out that hash. Now, it may be a little bit complicated, but we're starting to unravel the onion a little bit. All right. So, we build the proof network, implementing a nonce in the block until a value is found that gives the block's hash the required 0 bits. Once the CPU effort has been expended to make it satisfy the proof of work, the block cannot be changed without redoing the work, as later blocks are chained after it. The work to change the block would include redoing all the blocks after it. All right, so there's a block. There's your previous hash. So what's in the block header? This is the block header that they're showing here, or part of it. It's not even all of it. But this is the previous block. The previous hash is combined with the nonce, the and the transaction tree, in order to figure out the next block. Okay, or to figure out this block, and then that's cryptographically linked to the next block. So every block that's locked on here makes the previous blocks more secure. Makes the whole network and the whole system more secure. I'm taking a sip of coffee. All right, I'm going to read this word for word here because this is important. The proof of work also solves the problem of determining representation and majority decision making. If the majority were based on a 1 IP address to 1 vote, it could subvert. Move this up so y'all can see without my head being in the way. Subvert by anyone able to allocate many IPs. Proof of work is essentially 1 CPU, 1 vote. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. To modify a past block, an attacker would have to redo the proof of work of the blocks and all blocks after it, and then catch up and surpass the work of the honest nodes. And we show the probability of this slow attacker catching up on diminishing returns. Okay, so not likely to happen. All right. And where do I have? Somewhere in here I have to know. Yeah, so we do our demo right at the network section. Let's take a look for questions. Where can I find this info? Dale, I highlighted it when we started here. Let me show you real fast. You just go to bitcoin.org. Here's the link, bitcoin.org/Bitcoin PDF. If you just go to bitcoin.org, bitcoin.org. This is the bitcoin.org webpage. Go to introduction, white paper, and then whatever language you want. I would say English probably. I'll put it back in the chat one more time. And I would encourage you to follow along. I mean, anybody who's invested in Bitcoin, really, I'm gonna pause here and just a little bit of a soapbox item. Anybody who's who criticizes people who buy Bitcoin, every single time I've ever heard anybody criticize Bitcoin, it's because they don't understand Bitcoin. It's as simple as that. They just don't understand it, and so they're kind of scared of it, and they just think it's stupid, and so they criticize people who are involved in it. The problem is this is a very deep technological subject, right? And so this is the financial money of the internet, and so it takes some understanding. You don't have to have an insane understanding, but some understanding of technology. And I firmly believe that if you're investing in Bitcoin, you should have at least read this white paper once and have a basic understanding of it. And so that's what we're trying to accomplish today. And you guys can replay this later. A comp sci class is nice. You can replay this later and read through this and try to gain an understanding. There's a million really good videos on YouTube as well about covering this. All right, moving on. The network. I'm not going to go through the transaction steps. We're going to demonstrate that later. Nodes always consider the longest chain to be the correct one and will keep working on extending it. So just remember that. The longest chain always wins. So if somebody has 667,000 blocks and somebody else has 300,000 blocks, well, the 667,000 wins, regardless of whatever else we might think about it. If two nodes broadcast different versions of the next block simultaneously, some nodes may receive one or the other first. In that case, they work on the first one they received, but save the other branches in case it becomes longer. The tie will be broken when the next proof of work is found, or one branch becomes longer. The nodes that are working on the other branch will then switch to the longer one. All right, so there's two reasons this might happen. One, a malicious person can try to interject blocks that are contrary to the actual blockchain. The other is two miners solve the exact same block at the exact same time, or roughly the exact same time. This happens actually pretty often. And so because there are so many different possible combinations that can actually solve in any given block, it's common for two miners to solve the block roughly the same time. The truth is the more well-connected node is going to win. So what happens is if a miner that's really well-connected in, say, the United States solves the problem, and a miner that's very poorly connected in the middle of the Pacific solves the problem at the same time, the one who's poorly connected in the middle of the Pacific, he takes longer and communicates that information that he solved the block to less nodes in the network, whereas the one in the United States has communicated that much faster to much more nodes in the network. And then now there's a bifurcation in the network. So the larger network, though, is going to win the next block after that. So the well-connected network in the United States, say a peer of his in Europe then solves the next block faster than a peer of the person in the Pacific, say, solves that block. So as soon as, say, a peer of the one in the Pacific, that, say, in Japan, that received, he received both blocks. He's received the one from the Pacific miner slightly ahead of the one from the U.S. miner. When the European miner solves the problem before anybody in that network with the Pacific miner first, when that gets advertised to the network, that will break the tie fundamentally because they have a longer chain now. But this happens. This is a thing that happens on the network from time to time. It's very easily solved. It's just the longest chain always wins. So the more nodes you contact, the faster, the more likely you are to be on the winning chain. All right. If a node does not receive a block, it will request it when it receives the next block and realizes it missed one. All right. So now I have our demo here. This demo environment, I think, will help really drive this home. All right. Let's size this up so you see. Okay. So this represents a few key things that we've talked about here. This blockchain to IA demo. So our first person that's on the network is Satoshi himself. And he's mined the first block. Welcome to Blockchain Demo 2.0. And now let's go ahead and just add another block here. We're going to call this CTM Rocks, which is CTM is conquering the markets. All right. So I'm going to add CTM rocks in here as the next block that I mine. So what you'll see here, this is the hash, and so I needed at this level. It wasn't too difficult to mine. It was very easy, relatively speaking, to mine blocks at the Genesis block. The very first block was relatively easy, and it had 3 leading. So in this case, it has 3 leading zeros. And then the hashes, they get harder as time goes on. So we have 4 leading zeros here. This one will take more compute power to mine to find a hash, a nonce and tree combination that works to mine a block with 4 zeros. And that's linked cryptographically to the previous hash. And then you see the hash value here. So this hash value gets linked here, and this is the new hash. And this is the nonce. The 604 was the nonce that I used to come up with this number. And 1384 was the nonce. And the word nonce means it's an old term. It's actually from Old English. It just means one time. It's something that's used just one time. This is just a random number that's used one time to generate this hash. Okay? All right. So now we have the Genesis block, which is the very first block ever mined in the Bitcoin network, and then block number 1, the block after that. So let's add a peer. So Alberto, we're going to say he's actually Hal Finney. This is maybe Alberto, Hal's second pseudonym here. So we're going to go over to Alberto. What he sees is he's got the Genesis block. That's all he's ever seen. He's never seen, so Satoshi's mined a block. He doesn't know anything about it. All he knows about is the Genesis block. But now we're going to peer Alberto with Satoshi. All right. So now you see here in Alberto, this is a Bitcoin miner / full node, right? Now you see that he's got this first block of CTM rocks in here that we had. Same data, same exact hash, same data. If you look at the communication between Satoshi and Alberto came online. Alberto connected to Satoshi. He's asking Satoshi for the latest block. Satoshi requests the latest block from us as well, so peers share both ways. Satoshi sends the latest block. We sent Satoshi the latest block, and Satoshi sent us the latest block. And then what we found out was Satoshi's block previous hash is equal to latest block hash, append received block to blockchain. So basically, Satoshi had a longer chain than we had, an additional block that we didn't have. Now if we go over here to Satoshi, when Alberto joined him, Alberto has connected to you, asking Alberto. So Satoshi asked Alberto for the latest block, and then Alberto also sent over his block. Alberto's latest block index is not longer than the latest block index do nothing. So basically, Alberto had a shorter chain than I did, so I'm not going to do anything. And so we sent some stuff back and forth. Now, say Alberto is really Hal. So Hal's first block. So Hal now mines a block. So Hal finds the next one. And at this block, the difficulty was 3. So I got 3 zeros here. And this is a nonce that I used to calculate this hash based on the transactions. So the transactions are what basically are what form the tree. So the 2 things that you're combining again to come up with this hash are basically the transactions and the nonce. You're monkeying with this nonce number to find out a number that'll generate this hash. So Hal did it. Hal found the next block. So now if we go over here, we'll see we again sending latest block to Satoshi. Satoshi sent his latest block. Yeah, so we sent our latest block to Satoshi, and he sent over his. Satoshi's latest block index is not longer do nothing. Basically, because I mined this, when Satoshi sent his back, all he had was these two, so I didn't do anything. But Satoshi will say Alberto's block is equal to the latest block, previous hash is equal to the latest block, append received block to blockchain. So basically, he's saying that, okay, Alberto had one more block than I had, which was validated, so I'm going to add it to my chain. So now we've got 2 peers. We're going to pause here and go back to the white paper. We've got 2 peers here that now agree. We've got 3 blocks in the original blockchain. We've got Satoshi, and if I could rename this guy, I don't know if you can rename him, it'd be great. And Hal. Hal Finney, who's going by Alberto here. All right, moving on to back to our white paper. I'm going to pause. Any questions? I will let me put this blockchain demo and a link in here if y'all want to monkey with it. I'm trying not to get too distracted. All right. Here's the incentive for the network. By convention, the first transaction in a block is a special transaction that starts a new coin owned by the creator of the block. All right. So when everybody knows the miner's reward, when a new block is mined, the miner, whoever solved that problem and got that hash with those zeros, gets the reward. And right now it's 6.25. It was 12 back in May. That got cut from 12 to 6.25. Every it was 12.5 and down to 6.25. Every roughly 4 years, that reward gets halved. So the reward includes both and that's called the Coinbase. That's coming from the Coinbase. So the website Coinbase got its name from this incentive system, right? So the miner is rewarded from the Coinbase of all the coins of that Bitcoin will ever have, and at some point that will end, and it'll just be the transaction fees. We'll talk more about that. All right. So this provides a way to initially distribute coins into circulation, and it provides an incentive for the nodes. There is no central authority to issue them, not in Bitcoin. There is an XRP, a central authority that issued them, got them in some hot water, but not in Bitcoin. The steady addition of constant amounts of new coins is analogous to gold miners expending resources to add gold to circulation. In our case, it is CPU time and electricity that is expended. The incentive can also be funded with transaction fees. So whenever you send money on the Bitcoin network, I think everybody knows that there's a small transaction fee. And actually, the way that works is if I'm going to send you 1 Bitcoin or 1 point, what I would do is I would actually send you like 0.9999997 Bitcoin or something, and then whatever's left over goes to the miner, right? So there's a discrepancy between what I'm sending and the total value of the transaction, which then goes to the miner. So that's how that's calculated. And it's calculated based not on the trend. So another thing, just keep in mind, we'll talk about this when we look at the demo. Whenever you pay for your transactions, it's on the amount of data that's in that transaction, not the size of the transaction. So if I send 1,000 Bitcoin, or I send a fraction of a Bitcoin, I'm not paying the network to process a transaction based on the size, the amount of Bitcoin I'm sending. It's purely based on the size of the data in the block or in that transaction. Anyway, we'll talk. Well, you'll see that when we pull up the demo. In our case, it is CPU time. Okay. If the output value of a transaction is less than the input value, the difference in transaction fee is added to the incentive value of the block containing the transaction. That's what I talked about earlier. So there's a difference in values. The output value of the transaction is different than the input value, and that's added to the incentive. The incentive. So the bigger value, the bigger delta that you leave, the more money that you leave for the miner, basically, the faster your transaction will get processed. So you can, if you have very low priority transactions, and I think we'll see that here in a minute, I'll pull that up. If you have low value transactions, you can give it a lower fee, and it just takes longer for that to be validated on the network. All right, the incentive transition entirely to transactions. Okay, so once all the coins have entered circulation, the incentive will be entirely transaction fees. So miners will just get the transaction fees. They will no longer get, like in the year 2100 something, whenever that happens. It'll be completely inflation free. The incentive may help encourage nodes to stay honest. If a greedy attacker is able to assemble more CPU power than all the honest nodes, he would have to choose between using it to defraud people by stealing his payments or using it to generate new coins. He ought to find it more profitable to play by the rules, since rules that favor him, notice this is in British, so whoever this is from a British Commonwealth, whoever's writing this version of it. This part of it was written by somebody from a British Commonwealth. Favor him with new coins that everyone else combined to undermine the system, the validity of his own wealth. All right, so basically, if you do a 51% attack, if you are able to amass 51% of the compute resources needed to attack the network, in theory, you should just mine Bitcoin, because it's probably a lot more profitable than trying to attack the network and collapsing the value of Bitcoin and completely ruining the investment you made to get that much mining power. Yeah, you like that, Kevin, the XRP bird? All right, reclaiming disk space. So spent transactions can be discarded. So this is just some technical stuff that people that are buying Bitcoin don't really need to know about. But this shows you the tree that I was talking about earlier. So the values that the miners are messing with it's how it builds this tree. to get this root hash and the nonce and the previous. Those are the two things it's monkeying with. It's how it organizes this tree, and thus adjusting the root hash. And then it's what it's doing is building a root hash. So it's building a tree. It's building a root hash, and it's going through all the nonce values until it finds. It sees if it can find that hash with the zeros, and if it doesn't, going through the entire list of 4 billion nonce values, it has to recomputate this root hash by reorganizing this tree. That's what miners are doing. And so it takes, obviously if it takes me 8 billion tries of monkeying with this nonce to validate if this root hash is going to work for building a hash with that many leading zeros, if I have to try 8 billion times, it's a lot. And then if 8 billion doesn't work, I gotta start all over again with another root hash. And there's almost unlimited ways to build this, or a very large number of ways to build this root hash based on how I organize a tree. I'll be right back 1 second. You can see on the screen I've got like the sun right in my eyes. It just hit a spot. All right, sorry about that interruption. Yeah, the sun just like right in my eyes. I can't see anything. Okay, so. You guys don't need to know much about the technical reclaiming disk space. Okay. Simplified payment verification. How far along are we? 43 minutes. Very good. I have a note. When do we get into the rest of our... Yeah, let's just read through this. Let's turn through this, and then we'll get back to our demos. Simplified payment verifications. It is possible to verify payments without running a full network node. Users only need to keep a copy. So also note, if you know a little bit about Bitcoin, you'll know that there's miners and there's full nodes. And they're different things now. When Satoshi wrote this, he had the vision that, and he didn't know that ASICs and all these high-powered mining nodes would be a thing at some point, and that we'd end up splitting the network to be miners and full nodes. But full nodes are just verifying transactions, and they keep a copy of the ledger, and they verify transactions. They're not trying to compete to solve the next block. And miners are the machines that are trying to solve the next block. So when he says full node here, he means a miner. So a user only needs to keep a copy of the block's headers along his proof of work chain, which he can get by querying the network nodes until he's convinced along his chain to obtain the Merkle branch. So that's this branch we're talking about, the Merkle root. So how you organize the transactions in a block is what gives you the Merkle root, and then you calculate that root hash based on that tree. It's kind of complicated. I don't think you don't need to understand that. You just need to know that miners are monkeying with how they build this tree of all the transactions and the nonce value. They're constantly just churning through the 8 billion nonce possibilities, trying to find the right combination of things. Or one of nearly infinite combinations that will work. It's really hard to find one that will. It takes about 10 minutes for the whole Bitcoin network for somebody to find one on average. And that difficulty is changed every 2 weeks. The network assesses the hash power of the network and adjusts that difficulty accordingly. So, but to obtain the Merkle branch, linking the transactions to the block is time-stamped in. All right. So this is this is basically saying you don't have to run a full mining node just to be able to verify transactions. And this is nowadays we use the full node we call a miner, and then what this process of validators are doing we call full nodes. So kind of change the terminology. All right. Let's move on here for the sake of time. Combining and splitting value. So basically you can have multiple transactions in a single, you can have multiple inputs and outputs in a single transactions. So impossible to handle coins individually. It would be unwieldy to make a separate transaction for every cent in a transfer. To allow for value to be split, combined transactions contain multiple inputs and outputs. So you can have multiple wallets sending to multiple wallets in a single transaction if you want. It's not super common for everyday people to be doing that, but for larger transactions and more complicated things, automated transactions, that happens a lot. Normally you're just sending it. Now, I guess if you send it from an exchange, that's another thing. So if you're like on an exchange and you're sending to your own private wallet address, the exchange can pull from 3 or 4 wallet addresses to send to your one wallet address your funds. All right, privacy. The traditional banking model achieves a level of privacy by limiting access to the parties involved in the trusted third party. The necessity to announce all transactions publicly precludes this method, but privacy can still be maintained by breaking the flow of information in another place, by keeping public keys anonymous. So basically what they're saying is that we have to announce, again, it's a public ledger, we have to announce all transactions to the whole network, but you can keep your public keys anonymous in theory. Now obviously this is written long before regulation came around, and this is not really something that, you know, it's more and more difficult to make this happen these days. You have to already have Bitcoin somewhere, somehow. Pretty much every on-ramp nowadays makes you sign up with some information. It's very difficult to buy fresh Bitcoin on the network without, you know, announcing who you are. The public can see that someone is sending an amount to someone else, but without the information linking the transaction to anyone. This is similar to the, so I think they do say in here that they do acknowledge that if you basically look at it long enough, you can kind of figure out who sent what where. Yeah, here it is right here. An additional firewall. A new key pair should be used for each transaction to keep them from being linked to a common owner. Some linking is still unavoidable with multi-input transactions, which necessarily reveals that the inputs are owned by the same owner. If the owner of the key is revealed, linking could reveal other transactions that belong to the same owner. And the reality is regulation is kind of forcing this anyway. All right, I had a note here to get back to our demo. Let's read this little bit here, and we'll get back to the demo. We'll talk about bad actors. Calculations. We consider the scenario of an attacker trying to generate an alternate chain faster than the honest chain. Even if this is accomplished, it does not throw the system into arbitrary changes, such as creating value out of thin air, taking money that never belonged to the attacker. Oh yeah, I meant to delete that note. So, an attacker can only try to change one of his own transactions to take back money he recently spent. Okay? So, because of how these blocks are linked together in history, you can't if you were able to attack the network, you can't go back in time and have all the transactions say that the destination is you. Now, another thing, just a small note, like an attacker, something that people think can happen is not possible, because the way that the ledger works, it's unspent transaction outputs. So you have to have received Bitcoin before you can then go spend them, right? So you can't just tell the network that I now own all the Bitcoin, because you have to have a record of transactions flowing into you. So in theory, an attacker could go back in time and change the recipient of a bunch of transactions to himself, get a bunch of Bitcoin. But the network would consider that completely invalid because of the way that the transactions are linked. And so the attacker would have to resolve with a brand new hash, because any input, anything that you change about that block, any transaction you change, you have to start. You can't use the same nonce and Merkle tree to find that. You have to create a whole new one. So the attacker would have to recreate the whole chain and solve it faster than the main network, which would take it would be impossible, basically. So an attacker, so basically all that they can really do is invalid. So he can make a transaction, get something back, and then try to invalidate that transaction. That's the best an attacker can really do. And then this next note, this probability drops exponentially as the number of blocks an attacker has to catch up with increases. With the odds against him, if he does not make a lucky lunge forward early, his chances become vanishingly small as he falls further behind. So let's go to our demo. Let's see what we're talking about here. All right. So we've had Satoshi and Alberto / Halfitty over here. They've been going to work while we've been talking, and Satoshi mined the next one. This is Crypto Trades and Techs rocks, CTT rocks. So we're going to add this block. All right. So now Satoshi and Hal got a third block in here, CTT rocks. All right. And so now these are all cryptographically linked. Okay. And now let's add another peer, Rai. Rai comes in here. Rai is just another good participant in the network. We see that when Rai joins, let's look at I connected. So I connected to my peer Alberto. We sent each other back and forth our latest blocks that we had. Alberto's chain is longer than my current chain, so I replaced my entire blockchain. So when I first joined, all I had was a Genesis block, and then Alberto has all this stuff here, or Satoshi, same thing, right? So Satoshi's latest block, yeah. So I first talked to Alberto. So when Ree talked to Alberto, Alberto's blockchain was longer, and I replaced my entire blockchain. Okay, so we've got 3 good actors, and let's do Rhee's first block. All right, so Rhee has now built a block here, and you'll see. So now we've got this chain going on here. Now, let's put a bad actor. All right, Callie is our bad actor. So Callie is trying to maliciously change something on the network. So say Callie goes and connects to Rhee and Alberto, but doesn't connect to Satoshi because she doesn't want to tip off that she's doing something malicious. But she tries to go after people she thinks are more vulnerable. All right, so Rhee downloads the entire block. Now, if Rhee goes back here and says, you know what? Not Rhee, sorry. Rhee's our good actor. Callie is trying to attack the network. So Callie says, all right, in the first block, I'm going to try to skim off some funds here. Notice that the hash changes. Notice the hash becomes red. As soon as I change anything, unless the input is CTM rocks, which is basically this term here is equivalent to all the transactions in that block. If I change anything about that block, as soon as I put a space in here, delete the exclamation point, I change anything about it, it breaks not only this hash, but it breaks every other hash because the linked hashes are all broken. So I have to recomputate that entire chain. So if I want to attack the network now, Callie rocks, and then I skim some funds off. All right, I have to solve this block just like everybody else had to. So I've now solved this block. And then if I want to do Callie steals coins. All right, so while I'm doing that, over here, Satoshi's mining another block. All right, so Satoshi mines another block, we're on block 5. And while I'm monkeying around with that, Hal mines another block. All right, so now we've got 6 blocks. And now Callie's in a trouble because she's seen 2 more blocks come in. And I've got to now solve. All right, so Callie steals coin. All right, so Callie, and so you know, on my block, Callie rocks, Callie steals coin. So I've solved 2 blocks. Callie trying to catch up now, trying to resolve this chain that she's got with her modified. So right here is where I stole coins. This is where I changed the chain. This is where I received some. I'm trying to catch up. And so now, as this chain gets longer on this side, so these 3 are mining, and I'm competing with these 3 basically to sign all these. Now, let's look at the communication that's happened. All right, so Rhee's chain is our CTM rocks, Hal's first block, CTT rocks. If we look at, you see here that every time Callie sends me a block, what am I doing? Callie's latest block is not longer. 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 Right? All right. So until Callie can solve all of these blocks with her modified ledger, and then catch up and pass us, I'm not going to accept her chain. Which she's not going to be able to do that because it's her competing against us 3, right? So that's not really going to be a possibility. Now, the other thing that happens is something called forks. Now I want to go over that real fast. So if we had, say, Nolly here wants to make Nolly's blockchain. Nala's blockchain. And it's a straight rip-off of Bitcoin. I'll make my own blockchain. All right. And I'm going to make it a lightweight blockchain. Something like maybe a light coin. It's a total rip-off. Light blockchain. I don't know if y'all know any type of light coins out there. Coins that are light. And so it's super easy for me to solve blocks faster. So now I'm going to go here, and I have my own little network. And I get way up here. What happens if I take, and I've got 14 blocks in my new lightweight blockchain. All right. So my my chain is longer than theirs. What happens if I pair with Callie? All right, so I say Callie's, I have a longer chain than Callie does, but what does Callie see? Nala's chain is invalid. Now, why would Nala, Nala's got a longer chain. Why is Nala's chain invalid? Because Nala changed the root of the chain. So this is what's called a fork. And so basically, this is a forked network. So this is like light chain would be a forked network, right? So Nala's forked the network and has a totally different network going on over here with a totally different structure, and I simply just see that as an invalid structure. If that makes sense. All right. So this Nala. So we've got Callie over here. So I guess let's take a valid. So if Nala tries to, well, you get the idea. I think everybody gets the idea here. Satoshi, Alberto, and Ree are our three good actors. Callie's our attacker, and Nala is the person trying to build out. We're going to disconnect from all these peers here because. So Nala's got Litecoin network going on here. We'll get them off. And then so Callie is not going to be able to catch up. It's Satoshi, Alberto, Ree. Let's add another good actor here. So Kate joins the network over here. She sees the same Genesis block. And she talks to... So say she talks to Callie first. Check this out too. So Callie's got... Oh, this demo is going to give me limited. It's going to mess up. Yeah, anyway. So Kate talks... Did I tell Kate to power with Ree first? I did. Anyway, so now we've got more participants on the network. So Kate should appear to multiples. And then Callie's over here by herself trying to modify the chain. She's got a long way to go to catch up. So as we have more valid participants, more miners join the network. The longer that chain gets, the harder it is for an attacker to outdo the rest of the network. Nice, Heath. All right, where are we at now? Where are we at on time? Well, we're at an hour. All right, guys, let's try to wrap this up here. I hope y'all found this beneficial. I hope that blockchain demo gave you... We're pretty much done. So let's just get to the conclusion of the original white paper so you can say you've read it, been through it. So we've been through simplified payments, calculations, and conclusion. We have proposed a system for electronic transactions without relying on trust. We started with the usual framework of coins made from digital signatures, which provides strong control of ownership but is incomplete without a way to prevent double spending. To solve this, we propose a peer-to-peer network using proof of work to record a public history of transactions that becomes quickly computationally impractical for an attacker to change if honest nodes control a majority of CPU power. The network is robust in its unstructured simplicity. This is the key. This is what makes Bitcoin so strong, is it's actually extremely simple. Nodes work all at once with little coordination. They do not need to be identified since messages are not routed to any particular place and only need to be delivered on a best effort basis. Nodes can leave and rejoin the network at will, accepting proof of work chain as proof of what happened while they were gone. They vote with their CPU power, expressing their acceptance of valid blocks by working to extend them, rejecting invalid blocks by refusing to work on them. Any needed rules and incentives can be enforced with this consensus. Here's your word. That's finally where they put the word consensus mechanism. I didn't highlight that, but that's the consensus. All right.